All right. So thank you with the introduction. I would like to start this talk with two questions. First question is, why do we care about quantum computing at all? And in my opinion, the answer to that question is that we do because quantum computing is really nice. In the sense that over the past 30 years, this field of research has shown us time and again how quantum algorithms can vastly outperform classical ones, sometimes even achieving to tackle classically intractable problems. And contributions in this sense really span dozens of algorithms with far-reaching applications in many different fields. Which brings us to the second question. If this is the case, then where are these far-reaching applications? Like, why don't we see them out there in the wild, in the real world? And the answer to that question is that quantum computing is also really, really hard, in the sense that building, operating, and maintaining quantum hardware is extremely expensive and technically challenging, and therefore the quantum computers that we have are very limited in terms of computational resources and also in terms of reliability. Which means that although we do have really nice quantum algorithms, it's usually extremely hard to run them on the quantum computers that we have. Which means that we must be very careful with the resource requirements of algorithms, and we need to be very careful when we analyze the resource requirements of these algorithms. And this need is what motivates ultimately this work. But before we get into that, a little bit of basics. I'm sure you all now know what a quantum circuit is after Matthew's talk. But for the sake of this talk, you can just think of quantum circuits as diagrams such as this one. If we want to reason about the resource requirements of the computations associated to a quantum circuit, we must look at the circuit size. And there are varying notions of circuit size. For example, the width of a circuit is defined as the maximum number of wires that are active at any point in the circuit and corresponds to basically the memory requirements of the corresponding quantum computation. Whereas the gate count of the circuit is defined on the number of gates in the circuit and represents a sort of runtime requirement of the computation. A more refined metric in this sense is depth, which is defined as the maximum number of gates encountered on any path from an input to an output of the circuit, and this represents a sort of parallel runtime requirement of the quantum computation. And I told you that quantum computers are relatively limited, and this means that they can only run circuits up to a relatively small size. But what's more interesting is that different architectures, that is, different technologies, actually vary wildly in terms of what which of these metrics is the actual bottleneck of the computation. So for example, you could have an architecture that runs a very wide circuit because it has many qubits, but cannot run a deep computation because its qubits are not reliable. Or you could have an architecture that implements error correction, and so it has a few very robust logical qubits and can run deep circuits, but not wide circuits. And of course, there are tools to estimate, to check the size of a circuit and to optimize the size of a circuit. But let's look at how this translates to the analysis of quantum algorithms. Because of course, like a quantum algorithm is not implemented by a single circuit, but rather by a family of circuits, which contains a different circuit for every possible input size to the algorithm. The problem here is that as the input size grows, so does the size of the circuit that represents the applicable computation. And this means that if you're given a quantum architecture, there comes a point where the input size becomes too big for the quantum architecture to actually execute the corresponding circuit. And what we want to know when we're talking about the resource requirements of a quantum algorithm is we want to know where this cutoff point is exactly. So what is the maximum input size that we can run the algorithm on a given architecture? Of course, this is a problem that cannot be solved by looking at the individual circuit. We must look at the circuit family as a whole, and specifically at what generates this circuit family, which usually is a program written in a domain-specific language called the Quantum Circuit Description Language, or QCDL, which runs on a classical computer and produces different members of the circuit family depending on some classical parameters, such as, for example, the size of the input. And so what we want really is static analysis techniques that can take as input one of these programs and output upper bounds on the size of the circuits that these programs build. These upper bounds should be parametric, for example, on the size of the input, and they should also be concrete, so as to have close control over the resources. And our contribution is precisely in this sense, and our target language is the Quipper language. So Quipper is a higher-order functional QCDL embedded in Haskell. It is designed with the goal of being scalable and practical, which means that it is designed with the intent in mind of implementing real-world quantum algorithms, which translate to circuits that are very big and very complex. The theory of Quipper is usually studied through a family of languages that are based on the proto-Quipper calculus, which in a nutshell is a linear effectual lambda calculus with bespoke constructs to describe and manipulate circuits. What I mean by that is that a proto-Quipper term is always meant to be executed together with a quantum circuit, which provides the wires that the term can manipulate and append gates to. These wires are identified by special values which we call wire labels, or just labels. And the circuit built by a term M can be boxed and turned into a piece of data that we call a boxed circuit. And this is relevant because we can copy boxed circuits and reuse them in describing more complex circuits by applying these boxed circuits to the underlying circuit. So for example, a term such as this one applies the Hadamard gate represented by a boxed circuit H to a qubit labeled Q0. And if we have a circuit with one such qubit labeled Q0, we can run this configuration, and what apply H to Q0 does is emit a Hadamard gate to the circuit and evaluate it to the output wire label of the gate. Okay, so this was proto-Quipper in a nutshell. Proto-Quipper's type system is really nice in that it guarantees many safety guarantees at compile time, but it does pretty much nothing in terms of resource analysis. So what we did was we extended the proto-Quipper type system with type refinements and effects to obtain a calculus that we call the resource-aware proto-Quipper, or proto-Quipper array. And what we did was we annotated the types of proto-Quipper with quantitative information regarding the size of the circuits built by programs of that type. So for example, we have the type of functions that build circuits of size at most I in the spirit of types and effects. We have the type for circuits of size at most I, and we have dependent sized lists. And all of these annotations are what we call index terms, come from a language of what we call index terms or indices. And they are basically arithmetic expressions on natural numbers and index variables, which are a special kind of variable that types and effects are allowed to depend on. Speaking of effects, proto-Quipper array revolves around a typing judgment of this form, which tells us that for all assignments of the natural numbers to the index variables in theta, under typing context gamma and label context q, term M as type A and builds a circuit of size at most I. Here q is what we call a label context and contains the wire labels that are made available by the underlying circuit. But more importantly, theta is a set of index variables which represent the classical parameters of the circuit building process, such as, for example, the input size of the circuit. And because I can depend on these variables, the effect annotation is allowed to depend on these variables, we effectively have that I represents a concrete parametric upper bound on the size of the circuits described by M, which is exactly what we wanted. So this is nice. You will notice that I used a very vague notion of size in these couple slides, and this is because our type system is actually agnostic to the actual size metric being used for analysis, being analyzed. Specifically, we want to be as generic as possible, so we endow the language of indices with what we call abstract resource operators, which basically represent the evolution of an unknown size metric under certain conditions. For example, I star j, which we pronounce usually I sequence j, describes the size of a circuit obtained by composing in sequence a circuit of size I and a circuit of size j. And this is an example of how we use these abstract operators to carry out a generic resource analysis. In a let expression, if M builds a circuit of size I and N builds a circuit of size j, then the overall let expression builds a circuit of size I parallel the size of the wires that are not consumed by M sequence j. Okay, and this generic approach allows us to, depending on how we interpret these abstract operators, allows us to analyze various metrics, for example, width and gate count. It doesn't allow us, however, to deal with depth for the simple reason that, on one hand, gate count and width are what we call global size metrics. That is, they are properties of circuits as a whole, and thus are very amenable to a compositional treatment with effects. On the other hand, depth is not a global metric. It is what we call a local metric, in the sense that depth is a property of individual wires at the fundamental level, as we already saw in the introduction. Of course, we can take the maximum of the depth of all the wires in a circuit to obtain the depth of the overall circuit, but this is just an aggregation of a property that is fundamentally a property of wires. So how do we deal with this? What we do is we extend our system of type refinements, and we annotate wire types with information regarding the local metrics associated to the corresponding wire. So for example, if we are talking about depth, qubit 0 would be the type of a qubit wire at depth 0. So for example, a freshly initialized qubit. If we take a single qubit gate, it might have a type like this one, which tells us that it takes as input a qubit at depth d and outputs a qubit at depth d plus 1 for any d. And you can see how this use of index variables allows us to express local metrics in a functional fashion. And this is something that is pervasive in our work. In particular, the final form of our tapping judgment includes a context containing the index variables that we use to encode the functions in the judgments. And what we do is we annotate the wire types in Q, which we recall are the wire labels that come from the underlying circuit and which become the input of the circuit built by M. We annotate the wire types in Q with variables in Xi, representing the unknown local metric associated to the inputs of the circuit built by M. And we annotate the wire types in A, which represent the outputs of the circuit built by M, with indices built from the same variables. So we can achieve a form of dependency and express local metrics as a function. Of course, we want to be as generic as possible with local metrics also, which is why we extend the collection of abstract resource operators with a new operator for local metrics. And these symbols, these abstract operators, are interpreted by what we call a resource metric interpretation, or an RMI. An RMI becomes a parameter of the type derivation, and different RMIs define different instances of proto-Quipper array, which derive different judgments and thus are capable of analyzing different kinds of resources, different notions of circuit size. Talking about correctness, the actual size of a circuit is given to us via a function defined recursively on the structure of circuits, which we call a recursive circuit metric, or RCM. And we say that the proto-Quipper array instance is correct with respect to an underlying RCM mu, when basically the upper bounds that it derives for a term M are sound over approximations of the actual size of the circuit built by M as dictated by mu. And the general result that we have in this sense is that the proto-Quipper array instance obtained from an RMI T is correct with respect to an RCM mu if T is coherent with mu. What does this mean? We say, that an RMI T is coherent with an RCM mu when a small set of inequalities hold that basically tell us that T over approximates the recursive definition of mu. Such as, for example, the actual size of the empty circuit is over approximated by the null size abstract index, and so on and so forth. Unfortunately, I do not have enough time to go into details about coherence. Besides the theoretical results. We also have a Haskell implementation of proto-Quipper arrays type system in the form of an open source static analysis tool named QuRA. QuRA takes as input a program written in a variant of proto-Quipper. In this case, in this example, this is an implementation. This program implements the QFT, or quantum Fourier transform algorithm, as a function. And QuRA gives us a type for this function, which tells us something about the size of the circuits it builds. This type is in this case, we asked QuRA for a width and depth analysis. And what QuRA tells us through this type is that for every input size n, this function takes as input a list of n qubits, builds a circuit of width at most n, and returns n qubits. And as for depth, the same type tells us that for every input depth d, this function takes as input n qubits at depth d, and returns n qubits, where the ith qubit is at depth d plus n plus I. And if you run if you do a couple of computations with pen and paper, you'll find that these bounds are not only sound in this case, but they're also exact for the QFT. And QuRA is capable of deriving these bounds automatically, or mostly automatically, thanks to SMT solvers. In conclusion, our contribution is a type and effect system that can derive concrete parametric upper bounds on the size of the circuits built by a QCDL program, a proof of total correctness for this type system, and an implementation in the form of the QuRA tool. What remains to be done is find a better, come up with the notational semantics for proto-Quipper array. And notational semantics is something that all proto-Quipper variants, mostly all proto-Quipper variants have, and we still don't have one. And also developing a more extensive benchmark of the QuRA tool. So implementing more algorithms and verifying more algorithms with our tool. Before I conclude, I want to briefly mention that I very recently finished my PhD, and I'm currently on the job market. So I really look forward to discussing potential work opportunities with fellow researchers here at POPL in the following days. And with this, I'm done. Thank you so much for your attention.
So we have time for one or two quick questions. Raise your hand right there. I have one. The SMT solver can derive bounds mostly automatically. What was the mostly caveat there?
The mostly is that we still rely on some annotations in the source code, especially for like local metrics. Global metrics, we can mostly defer everything to the SMT solver, but with the local metrics, we have to like keep track of some things in the code. So we haven't encountered yet instances where the SMT solver hangs, but this still relies on quite some annotations in the code. Not really, because there are like different ways of expressing the same resource requirements, and so there isn't a notion of principal type.
How do you choose which alternative in your logical relations?
In some occasions, they are like equivalent, so it doesn't matter. Otherwise, I do not really have an answer for this, because I haven't looked into what kind of type is actually returned when there isn't a principal type.
So actually, I think we're running a little bit behind because of our technical snafus, so let's thank Andrea again.